In the last class we studied the dual simplex algorithm, where we solved a minimization problem with all greater than or equal to constraints without using artificial variables. We also said that in the simplex algorithm, right through we ensured that the right hand side was greater than or equal to 0, which meant that the primal was feasible, and the Cj minus Zj's were, some of them were positive, indicating that the dual was infeasible. By entering the positive Cj minus Zj's, we ensured dual feasibility. So in the simplex we had primal feasibility and we moved towards dual feasibility, and then we got the optimum solution. In the dual simplex we had negative values on the right hand side, indicating that the primal could be infeasible, but the dual was always feasible. And then once we decided the leaving variable first and then the entering variable, we reached primal feasibility and hence optimum. So dual simplex ensured that the dual was always feasible and the primal was infeasible, and finally we brought it towards feasibility. Now let us look at a problem that is shown here. It is a maximization problem with two less than equal to constraints, one greater than or equal to constraint. The objective function also has a negative term. So let us first set up the simplex table without artificial variables. Ordinarily the second constraint, which had the greater than or equal to, would have resulted in a negative slack and therefore would have resulted in a artificial variable. Now we do not introduce the artificial variable, we retain the negative slack x5 and then we multiply with a minus 1 so that we get this identity matrix. Here using x4, x5, x6, and we can start the simplex table. Now when we start the simplex table, we realize that the right hand side values are positive, negative here and positive, indicating that the primal is infeasible. One of the variables has a negative value. We also calculate the Cj minus Zj to begin with x4, x5 and x6. There are 3 constraints. So with x4, x5 and x6 as basic variables, with 0 as the objective function contribution. So the Cj minus Zj's are 4, minus 1, 5, 0, 0 and 0. So to begin with, we realize that we have a situation, if we create a simplex table like this, we have a situation where the right hand sides are all of them are not greater than or equal to 0, the primal is infeasible. One of the Cj minus Zj also has negative, the rest of them have positive. So this positive indicates that the dual is also infeasible. So we have a situation, we have a solution where the primal is infeasible as well as the dual is infeasible. Till now in simplex we always maintain primal feasibility. In dual simplex we always maintain dual feasibility. But now we realize that we have neither of them satisfied. Can we still proceed and get a solution to the problem, or should we go through the big M method and artificial variable? The answer is we can proceed and do it, and we will show how to do it without adding the artificial variable, provided the problem has an optimum solution. So let us try and do this. So we could follow what is called the simplex way by first entering a positive Cj minus Zj and then finding a leaving variable, or we could do the what is called the dual simplex way by first leaving a variable that has a negative value. So first identifying the leaving variable and then identifying the entering variable. So we could do in either of the ways. So but right now we begin by doing it in the dual simplex way, which means we will first identify the leaving variable. So the variable x5 with the minus 40 is the variable that leaves first. So we have to find out the entering variable. Since we are doing it the dual simplex way, we have to find out the coefficient. There is only one negative, so we have to look at only negative Cj minus Zj values. Problem is a maximization, so we have to look at only the negative Cj minus Zj values. There is only one, and it has a negative coefficient in the pivot row. So there is only one candidate with a ratio of 1 by 8, and variable x2 is the only candidate, and that will enter. So we can now do the next iteration by replacing variable x5 with variable x2. So we have started it the dual simplex way, and by saying that x2 will replace x5. So we proceed to the next iteration. So I have shown the next iteration here. So to begin with, we started with this as the leaving variable, and then this as the entering variable. So let me also use this as an opportunity to explain a problem that has 3 constraints. So far we have solved all our examples with 2 constraints when we did either simplex or dual simplex. So this is our pivot element. So divide every element of the pivot row by the pivot element. So minus 5 divided by minus 8 will give us 5 by 8. I am highlighting every term that we are doing in this table. Minus 8 divided by minus 8 is 1. Minus 7 divided by minus 8 is 7 by 8. 0 divided by minus 8. 1 divided by minus 8 is minus 1 by 8, and 0. Minus 40 divided by minus 8 is plus 5. So we have written the new second row or the pivot row in the next iteration or the new iteration. Now this is called a dual simplex iteration, and since the pivot element is negative and the right hand side is also negative, in the next iteration we will get a positive value here, which is the purpose of having a negative pivot in a dual simplex iteration. Then we have to do the first row as well as the third row. Now to do the first row, we look at this element which is 4. Now we already have created a 1 here, we created a 1 here, which is the new pivot from the pivot element. So we look at this 4, and then we need a 0 there, because we have 3 constraints. Identity matrix is now 1 0 0 0 1 0 0 0 1. So according to x, under x4 we should have 1 0 0, under x2 we should have 0 1 0, under x6 we should have 0 0 1. So we now have a 1, so we should have a 0. 4 minus 4 times 1 is this 0. So we can write this first. So the first row minus 4 times the new second row is the row operation. So 3 minus 4 times 5 by 8, 3 minus 20 by 8, which is 4 by 8, which is 1 by 2. 5 minus 4 times 7 by 8, so 5 minus 28 by 8, 12 by 8, 3 by 2, so 3 by 2. So 1 minus 4 times 0 is 1. 0 minus 4 times minus 1 by 8 is plus half. 0 minus 4 times 0 is 0. 30 minus 4 times 520 is 10. So we have completed this row, the first row. Now we have to write the third row. The old value, the value is 6. So 6 minus 6 times 1 will give 0. So the rule is the new third row is the old third row minus 6 times the new pivot row or the new second row. So 6 minus 6 times 1 is 0. 4 minus 6 into 5 by 8. So 4 minus 30 by 8. 32 by 8 minus 30 by 8 is 2 by 8, which is 1 by 4. Of course 6 minus 6 times 1 is 0. 5 minus 6 times minus 1 by 4, 5 minus 6 times 7 by 8. So, 5 minus 42 by 8, 40 by 8 minus 42 by 8 is minus 2 by 8, which becomes minus 1 by 4. 0 minus 6 times 0 is 0. 0 minus 6 times minus 1 by 8 is plus 6 by 8, which is plus 3 by 4. 1 minus 6 times 0 is 1, and 36 minus 6 times 5, 30 is 6. So, this is the next solution. This is how we do the iterations when we have 3 constraints. Now, the basic variables are x4, x2, x6 in that order. You will find the identity matrix in that order 1 0 0, 0 1 0 and 0 0 1. Now, we find the Cj minus Zj values. So, there are 2 zeros here, so we do not have to do the multiplication. The minus 1 is the one that will contribute. So, the first one is 4 minus 5 by 8, 4 minus 4 plus 5 by 8, 4 minus 1 into 5 by 8, 4 plus 5 by 8, 32 plus 5, 37 by 8. The basic variables will have 0 as the Cj minus Zj, so we need not worry so much about it. Now, we look at the third one. So, 5 minus 1 into 7 by 8, 5 plus 7 by 8, which is 47 by 8. And the last one is 0 minus 1 into minus 1 by 8 will give us minus 1 by 8. If we want, we can calculate the objective function value, but we are not doing it. We could have done it, minus 5 is the value, but I have not shown it because I have one with a negative coefficient, but that does not mean anything. We can calculate the objective function and write it as minus 5, we can do that. So, now we realize that we have a iteration at the end of which some of the Cj minus Zj values are positive. It means we can proceed from the simplex way by entering x3, which has the largest positive coefficient. We look at the right hand side, now we realize that the right hand side is feasible, therefore, we cannot proceed the dual simplex way. So, in this iteration we can proceed only the simplex way, and therefore, we proceed in the simplex way by entering variable x3, which has the largest Cj minus Zj. So, we do that and we enter variable x3. Now, to find out the leaving variable, we do the simplex way. 10 divided by 3 by 2 is 20 by 3, 10 divided by 3 by 2 is 20 by 3, 5 divided by 7 by 8 is 40 by 7, 40 by 7 is less than 6, 20 by 3 is more than 6. So, 40 by 7 is the smaller one, and 40 by 7 will leave the solution. So, in the next iteration variable x3 will enter the solution and variable x2 will leave the solution. Now, that is shown here. I have shown a lot of iterations here. So, x3 has entered here and x2 had left. So, you see that x3 has entered the solution and there is no x2 in this. At the moment, I am not going to go through each and every one of the calculations. You can see the simplex table and you can proceed. Now, when we do this, the next iteration, which is the third iteration of this problem, you realize that x4, x3 and x6 are the basic variables. Now, when we complete the iteration, we have a solution. X4 is equal to 10 by 7, x3 is equal to 40 by 7 and x6 is equal to 52 by 7 with the objective function value 200 by 7. Now, the Cj minus Zj values are 3 by 7, minus 47 by 7 and 5 by 7 with x3, x4 and x6, which are the basic variables, having 0 as Cj minus Zj. So, we are interested in this positive Cj minus Zj, we are interested in this positive Cj minus Zj. Now again we realize that in this iteration the primal is feasible. So 10 by 7, 40 by 7, 52 by 7 is feasible, and therefore we cannot do the dual simplex way, we will do only the simplex way by entering variable x5 into the solution. Now to find out the leaving variable, 10 by 7 divided by 5 by 7 is 2, 52 by 7 divided by 5 by 7 is 52 by 5. So 10 by 7 variable x4 will leave the solution. Then we move to the next iteration. So x5 will enter, x4 will leave, you can see this, x5 has entered, x4 is not in the solution. Now the solution is x5 equal to 2, x3 equal to 6, x6 equal to 6, which is also feasible here. But continuing, we realize that there is one Cj minus Zj which is positive, therefore we do the simplex way, we cannot do the dual simplex way, we do the simplex way and then we enter x1 into the solution. When we enter x1 into the solution, x6 will leave the solution with minimum ratio of 6, therefore you realize x1 has now come into the solution in the place of x6. Now at the end of this iteration, you realize that the solution is x1 equal to 6, x3 equal to 12 by 5, x5 equal to 34 by 5 with objective function value equal to 36. Now the primal is feasible, 34 by 5, 12 by 5 and 6. Now we look at the Cj minus Zj values. The three basic variables which I am highlighting here, which I am showing here, the three basic variables are x1, x3 and x5. So x1 has a 0, x3 has a 0 and x5 has a 0 under the identity matrix. But if I look at the three non-basic variables, this has a minus 7, this has a 0, this has a minus 1. So no positive Cj minus Zj, algorithm terminates giving the optimum solution, which is x1 equal to 6, x3 equal to 12 by 5, x5 equal to 34 by 5 and objective function value equal to 36. The optimum has been reached here at this point when we have this solution with objective function equal to 36, the optimum has been reached. However, we observe something interesting happening, that a non-basic Cj minus Zj, which is corresponding to this variable, now has a 0, it is not negative, it has a 0. Now can we enter this is the other question. Now this phenomenon is called alternate optima. So when the optimum is reached, when all Cj minus Zj less than or equal to 0, I repeat, when all Cj minus Zj less than or equal to 0 and the optimum is reached, and if still a non-basic Cj minus Zj is 0, then it indicates alternate optimum. So we can enter that and look at the alternate solution. So if we enter this, then this variable will come in and variable x3 will leave, and if we do another simplex iteration, we realize that there is no increase in the objective function because it is an alternate optimum, and we find x1 is equal to 9 with z equal to 36. Also interesting that we realize that the Cj minus Zj are identical compared to the previous one, they will become identical. Once again if we see this, optimum is reached, but there is a non-basic Cj minus Zj with the 0 value. There is a non-basic Cj minus Zj with the 0 value. Non-basic because these values are not identity matrix. So non-basic Cj minus Zj greater than. So again if I enter x3, I will realize that x4 will leave the solution and x3 will come in, x4 will leave. I will get this solution, I will get the previous solution will now repeat. The previous solution will now repeat. So I have to understand that alternate optimum is happening and then I will terminate. So this is one way to solve a slightly larger problem, a 3 constraint problem, and this problem also helped us understand that alternate optima can happen. Now we can do this. To solve this problem, we actually started with the dual simplex way. Now we also said we could have started the simplex way. So this is the first table. Now instead of leaving this minus 40, we could have started the simplex way. So if we started the simplex way, then this variable x3 will come in because this has the largest Cj minus Zj. Now the ratios are 30 by 5 is 6. Here I do not find the ratio because the pivot element is negative. I will not find the ratio, and 36 by 5, 6 is smaller, so 6 will go. Now variable x3 will enter and variable x4 will leave. And if I do that, I come to this, and after 4 iterations or 3 iterations, I actually get this solution with 36. And once again you realize that there is this alternate optimum, and then we can do this and get the solution. So in the same problem, if we had started the dual simplex way first, in this example, if we started the dual simplex way first, we got the solution, but we did more iterations. When we did the simplex way, we also realized that in the next iteration, this minus 40 by itself was becoming feasible, and therefore there was no need to do the dual simplex way. So this also helps us understand that we could do either the simplex way or we could do the dual simplex way, but we will get the final solution with 36. Because there is alternate optimum, we can do the alternate optimum again, and we see the same thing occurring with an alternate solution of 36 and this variable coming in, and it will repeat. Now interestingly, there is a third way to also look at this problem. Now I could have done the simplex way, but interestingly, if I had done the simplex way, I would have normally gone ahead and entered the variable x3 because it has the largest Cj minus Zj. But instead, if I choose to enter variable x1, which does not have the largest Cj minus Zj, if I say any positive Cj minus Zj can enter, if any positive Cj minus Zj can enter, x1 will come in and x4 will go, and you realize that in one iteration we are able to get the optimum solution with z equal to 36. We get this solution with 9. Again alternate optima is indicated by the presence of this 0, and if we do the next iteration, we will get the other solution. So from this example we have understood a few things. 1, if we have a problem with mixed type of constraints, if the problem has a solution, then we need not add artificial variables, we can do a combination of simplex and dual simplex. There could be iterations where both are possible, we can take one of them and proceed. There could be iterations where only one is possible and we proceed in that way. A general guideline is, if both are possible, try the simplex thing first and not the dual simplex thing first, which means try to first enter a variable with a positive Cj minus Zj and then proceed. Only if it is absolutely necessary, there is no entering and only dual simplex iteration is possible, then do the dual simplex. The other thing we learned through this example is the presence of alternate optima. So when we have the optimum reached, all Cj minus Zj's are less than or equal to 0, and then we find that there is a non-basic Cj minus Zj with 0, then it indicates alternate optimum, and we will do that. The Cj minus Zj will repeat, and we could take either of these solutions. In fact, it is also true that when we have alternate optimum, we not only have these two solutions, we also have infinite alternate optimum solutions. But simplex algorithm, being an algorithm that looks at corner points, will give us only the corresponding corner points. Some more aspects of solving the dual and understanding the dual solution we will see in the next class.